Okay, so we're team 5 and we're going to present our Manchester final project. So basically, these are the 5 teams of our 5 members of our team: Daniel Reyes, Roberto, Jorge Nájera, Juan, and Jeffrey. Okay, so first of all, the introduction. The problem we want to solve is controlling the speed of a DC motor. One way is to use the open loop control by applying a voltage proportional to the desired speed, but this approach isn't robust against disturbances. It can correct the output if something changes. It lacks self-regulation, making it unreliable. So we introduce a closed loop controller, specifically a PID. This type of controller is widely used if we mathematically analyze the effect of adding proportional, integral, and derivative gains. We can prove that the error tends to zero over time. That means the actual velocity will eventually match our desired velocity, fulfilling our control objective. In this project, we'll implement the PID using ROS2, a middleware that helps us modularize and standardize robotic software. In other words, with ROS2, we can build a more organized, maintainable system. Okay, control. Let's check the control strategy before diving into ROS2. First, using a quadrature encoder, we measure the angular displacement of a motor shaft. By dividing the displacement by the time it took, we can calculate the instantaneous angular velocity, our target variable to control.
Okay, this measurement can be quite noisy, so we introduce a low-pass filter to smooth out the signal. In the frequency domain, output changes show up as high frequencies. By cutting off those high frequencies and keeping the lower ones, we get data that better represents the system's actual output. Next, we compute the error by subtracting the filter angular velocity, or where we are from the set point, where we want to be. We then apply the PID in its discrete time form. The result is a control output that we feed as a PWM signal into a motor driver. The driver then provides a voltage to the motor, influencing its angular velocity. We measure this new velocity closing the loop. Depending on the sign of the control signal, the motor driver adjusts the motor's direction.
Okay, so for the fine-tuning of the PID control, we use a manual heuristic-like approach. We simply, made by trial and error, adjust little adjustments in different orders to our PI and D gains. So first, we start with the proportional gains. We start with this since without maintaining the P, we scale the error as well as scaling the signal towards the desired outcome. So whenever we went over the necessary P gain, the error overly scaled, and it led to major oscillations. Then when we got a desirable or acceptable P gain, we then went to the I gain. This helped us eliminate steady-state error, ensuring the system can reach fully its desirable outcome. And then we use the D gain sparingly, since the system already has its own kind of damping, but the D gain allowed us to attenuate the oscillations made by the P gains. So rapid changes could be less aggressive. And so at the end, we got these 3 gains: the Kp for the constant of perpetual proportional at 30, the constant of integral at 20, and the constant for derivative at 0.5.
So it's time to look at our software architecture, and you can see an image on the right part of this presentation. And we can look at the setpoint node that publishes setpoint signals, and we can choose from a variety waveforms. Like we have options like sine, square, step, and other forms of signals. And we can update dynamically at runtime these different parameters of the signals. And all those signals are published on the setpoint topic. On the controller node, we have a micro ROS node running on a ESP32. And this node subscribes to the setpoint topic, performs PID calculation, and controls the motor accordingly. We also publish relevant debugging data, such as model output, error, model input, and all of this using a best effort quality of service, since absolute reliability isn't critical for the debugging tasks. And on the other hand, we have a quality of service reliable in our setpoint topic, because it's critical for us when controlling a real-world element, because we need to ensure it's always received correctly. And this node is working at a rate of 50 Hertz. The higher the frequency, it improves the controller to behave better, because it gathers more data about the system actual response. But we are limited by the executor spin time, which also handles the data from the teleoperator. So we can run the controller at a frequency faster than we can reliably collect new setpoint information.
Okay, so we are now going to see the result of the project. First, we introduce a sine wave. We can see that the motor output is closely following the set point. The error is small. The measurements can be noisy, as we said, but this is enough for our application. Now we change to a trapezoidal signal. Now we are going to use a ramp. Now we are going to see a sawtooth. We can see a little overshoot when the motor stops.